Hello, stats class. Here is lesson 11.1b. First, this is crooked, so I'll try to fix it. There, that's better. So what we've been learning about chi-square is specifically called a goodness of fit test. We have a hypothetical set of proportions for a specific categorical variable. And there's usually many categories. And we have a sample that we want to see if that sample came from a population that fits these proportions. See if our sample data comes from a population that fits those proportions that were given, and that's why it's called goodness of fit. How good is the fit between what we have and what we think we have? And so that's what we're learning how to do. There are other types of chi-square tests that we will learn in 11.2, so those are coming later. But today's the day I'm going to teach you about the plan stage, which is the conditions for this test, and then we'll do a full 4-step example. The conditions are almost the same as what we've been doing in the other chapters, and that's kind of comforting. In fact, 2 of them are exactly the same. First of all, random. It still has to be a random sample, or sometimes there's an exception to that rule, which I will tell you about. Random sample is usually given, or often this particular type of test is done with a non-random sample, and we know it's not random, but we want to see if it's representative of the population. So that's an interesting thing, that this is a useful way to check your sample and see if it's representative of your population according to whatever categorical variable you're interested in, often race or something like that. And sometimes that's okay to not have a random sample. That's weird. The independent condition is the same, so I'll do it next. There's only one sample to worry about, so we don't have to do the 2 separate samples thing or the 2 separate check the 10% rules. We're just checking the 10% rule once. The n has to be less than or equal to 10% of the population size. That's still true, but it's a lot easier than in chapter 10 when we had to check more than one thing for this. Remember, n is the sample size. You probably knew that. The one that has changed is the normal condition, because chi-squared is not normal. So, oh gosh, it's abnormal. That's crazy. There is no normal condition. There's something else instead. Because, as we talked about in 11.1a, chi-squared distributions are always skewed right. It's not supposed to be normal. And so instead, we're still going to check to see if our sample size is big enough. We're going to call it the large enough sample condition. I suppose we could have called it that before also, except it might not always be large enough. It might be just that it's normal and small. So just like in chapter 10, when we were doing proportions and we checked the expected number of successes and failures, we're going to do that with chi-squared also. We're going to check the expected counts. The expected counts. And because there's usually so many of them, they don't have to all be bigger than 10. That would be the n times p for whichever p we're looking at. All the np's, sample size times the proportions from our hypothetical list, have to all be bigger than 5 in this chapter instead of 10. So of course, if they're bigger than 10, that's also okay, but they don't have to be bigger than 10. And I've seen some books that say no more than 20% or less than 10. We're not doing that. We're just going to check, are they bigger than 5? In fact, technically, you only have to check the smallest one. And we'll talk about that when we do our example. Because if the smallest one is bigger than 5, then so are all the rest. All right, so let's do an example of the 4 steps. These are the conditions, all the rest of the steps we've talked about. So let's do a 4-step example. And we're going to talk about landlines. We have a random sample of landlines. In case you don't know what landlines are, it's the phone that connects to the wall with a cord instead of being a cell phone. Instead of a wireless phone, we have a random sample of landline owners in the US. And we're interested in seeing if their ages are the same as the ages in the US in general, or are they different? Are old people more likely to have landlines, which I think they probably are. And so we get this sample data that looks like this: age group 20 to 29. We're not going to do teenagers, sorry. Teenagers hardly ever have a landline of their own, although they did when I was a teenager. I had my No, I didn't have my own landline. I had to share with the family. Anyway, 141 and 30 to 39, 186. And we're just going to have some categories of ages. We could have, I suppose, done something with mean age. We're not doing that. We're doing categories because this is the chi-square chapter. So our sample is pretty big, 1,048 people in our sample. That's our sample data. And we want to know how this compares with the population of people in the US, and is it the same distribution of ages or not? So we gather some population information from the US Census. You can look up that information online and it's kind of interesting, and we're going to do the same categories. 60 plus, and we're going to look, if you look up those proportions, 19.1% of the US are 20 to 29 year olds, 21.5%, 21.1%, 15.5%, and 22.8%. And of course, this ought to add up to 100%. I hope it does. I didn't check. But we're comparing to see if these counts fit with these percents or not. Based on, I'm going to say we're testing to see if these distributions are the same. Does this fit with what we know about the population? And the goodness of fit test is what we're going to use for that, and we're going to do the 4 steps. So here's the beginning introduction to the problem. Is they would give you this data, they would give you this list of percents, or if you're doing a project, hint, hint, that's coming soon, you would be looking up this information and you'd be gathering this data, right? Okay, so step 1 is the state, and we have to state our hypotheses and our significance levels. So we're going to use an alpha of 0.05 because that's normal, and we're going to do our hypotheses. Remember, in this chapter, the hypotheses are usually written in words. So we could, if we wanted to, write out all 5 of these as our null hypothesis, and that's a pain, but what's usually done is it's written as a sentence. So let's go the age distribution for landline owners, people with a landline phone, matches the census proportions. So that is what our null hypothesis is. Our null hypothesis is that they're the same. That's the null, and this should have said different, not difference. The different is the alternate always. So the same is boring. Yeah, if it's the same, that's boring. That's the null is dull. Matches the census proportions given above. And that's what's usually done, is rather than list all 5 of them, rather than say the proportion of 20 to 29 year olds is this and the proportion of 30, usually it's matches the table given above. And that's just so much easier to just say that instead of writing them all out. Alternate. Do you know the alternate for this chapter? It's always the same, by the way, or at least it is until the very end when we change it. The alternate is always, for goodness of fit, at least one proportion is different. We don't care which one. We kind of suspect that it's going to be older people more likely, but yeah, at least one proportion is different. So at least one category is different than the population. And we're not going to list them all. We could, we're not going to. It's so much easier not to. All right, so the plan, what we're learning how to do right now is called a chi-square goodness of fit test. There are 2 other types of chi-square tests that we will learn later in the week. So you should tell me which kind you're doing. This one's called the goodness of fit. You could abbreviate it as GOF if you like. Totally up to you. Random. Well, yes, it says this is a random sample. Now, this is not a random sample from the whole US. It is a random sample of landline owners, but that is okay. So because it says that it's random, we're going to say given. And we want to know if landline owners are representative of the population or not. So you could add that if you want. I'm going to do large counts in a second. So large enough sample is my second condition that's replacing the normal condition. And I'm going to calculate my expected counts. Or better yet, I'm going to calculate the smallest expected count. So I'm going to say the smallest of my E values. And you're eventually going to have to calculate all of them, but I'm going to just do the smallest one for now. The smallest one would come from the smallest one of these. The smallest category of people is the 50 to 59-year-olds. I have no idea why that is, but the sample size is 1048 times the smallest proportion on your list, which is 0.155, and I would multiply those together and get 162.44, and yes, that's way bigger than 5. So this is a yes, because the smallest expected count is bigger than 5. So just a reminder that you don't have to do all of them right now. You will when you get to the second step, when you get to the, or the third step, I mean, when you get to the calculations, you're going to find them all, but you don't have to yet. And then, is it independent? That's the 10% rule. And I'm asking myself, is 1048 less than 10% of all landline owners in the US? Yes, it is. And remember, I am super picky about this condition because I've had so many students in the past just write yes, n is less than 10%. And then they think they're done. You have to have the number for me, and you have to have of what? Of all landline owners in the US. All right, no problem. That might not always be true, by the way. In the future, we're going to go to more and more cell phones. Do calculations. Now, there's a calculator way. There are 2 calculator ways that I'm going to talk about today, but for AP purposes and for me, you need to write out some of the work. Now, there are 5 categories. And so officially, we're going to add 5 things together. You do not have to write out all of those 5 things, but you do have to write out some of them. So I'm going to write the formula first, observed, sum of the observed minus the expected squared over the expected. We already saw that formula in the last lesson, but then you're going to plug in some of the numbers to prove you know what's going on. And so that's what I require, and also the AP test requires this. So we're going to take the first observed count, which is 141, and we're going to subtract its expected count, which I'll calculate in just a moment, and divide by the expected count. So I'll come back to that in a minute. And then I'm going to take my second one, which is 186, and subtract its expected count and divide by the expected count. You need, for me and for AP, you need to write out at least 2 of these. And then you have permission to put plus ... to imply that you now have proved you know how to do it, and you're going to let your calculator do the rest. So here's how you do it on the calculator. I'm going to show you my lists that I have right now, which are not right, not yet. I have my counts, observed counts in list 1. List 2, here's a common mistake students make. they put the proportions in list 2, which is a step along the way, sure, but it's not what I need for expected counts. These are not expected counts. These are proportions. So remember, the hypothesis is about the proportions, but the calculations are based on counts. I have to convert these into counts. So I'm going to do that in list 3, actually. And I'm going to say that I want list 2 to get multiplied by my sample size, which was 1048. So I'm going to multiply list 2 times 1048, and that gives me my expected counts. Now remember, I already calculated one of them, the 162.44. I've already did that one. Now I have all of them, which is what I need for this calculation. So I have all of the counts now, and I can write the first 2 here to show my work. 200.17, and then this is 225.32. I'm just reading those numbers off of my list 3. I could also put these into list 2 rather than having that extra step. So now I've proven that I know how to do it, and now I'm going to finish doing it. And I'm going to do it first the way we did it in the notes on 11.1a, with the calculator list method, and then I'll show you an even better shortcut. And then just in case somebody needs it, this number comes from 1048 times the 0.191. This number comes from 1048 times the 0.215 that came from my table up above. So they're just taking these percents and multiplying by the sample size. Okay, so I'm going to show you 2 ways to get chi-squared. Method 1 is what we did on whatever day that was in 11.1a, where we took our next list, whatever list it is, and tell it to do the formula. So you go to the very top, you parentheses list 1 minus, this time the expected are in list 3, that shouldn't bother me, divided by list 3. You could do that to get your contributions to chi-squared and then add them up by doing the sum. So remember calculator method number 1. Is you put your observed into list 1. In this case, I put my expected into list 3. Doesn't really matter. And then on list 4, I tell it to do list 1 minus list 3 squared over list 3. That's what we talked about already. And then I add up the sum of list 4 by doing, back to the home screen, stat, actually second stat, math, sum, list 4. Now, there might be a better way than that. Some of you are going to have to do it this way because you won't have the shortcut that I'm about to show you. So basically, the sum of list 4 came from second stat math. We talked about that method already, and I wanted to remind you of it. I got a chi-square value of 48.17. And then I'm going to tell you about calculator method 2. I hope it doesn't really annoy you that method 1 is on the right and method 2 is on the left, but it doesn't matter. Calculator method 2 is, some calculators have a shortcut for this that's even better than the shortcut I just did, and it is in stat tests. So take a look at your stat tests menu and go down and see if you can find any chi-square stuff. I see 2 chi-square things on my list because I'm using a TI-84 right now. I have a chi-square test and I have a chi-square GOF test. Guess which one I want? GOF test. If your calculator does not have the GOF test, you are going to do this method. And that's okay. But if your calculator, if you're lucky to have the better calculator that has the newer stuff on it, it has the chi-square GOF test in stat tests. That's amazing. It's on the TI-84s. It might only be the more recent 84s. So you're going to do this if you have an 83 or if you have some other type of calculator. You may or may not have it. I don't know. But then it asks you to say, where did you store your observed and expected? Right now, my observed is in list 1 and my expected is in list 3. And I have to also tell it DF. I don't know why it can't figure that out for itself, because DF should be available from the lists. But we have 5 categories, and so DF is 4. So you have to tell it which lists and DF. And DF is 4 in this case, and then we hit calculate, and it does the magic. Amazing. So it tells me the 48.17. It tells me my p-value, which if you're doing it method 1, you would be doing chi-square CDF to find the p-value. That's okay if we have to do that. So do I have room to write this? Not really. I'm going to make room. 999 and DF is 4. There you go. So you could find the p-value by doing that, or you could find the p-value with the shortcut. It is really, really, really small. It is 8.69 times 10 to the negative 10th. Super small. Officially, that is 0.00000. It's 9 zeros. 869, in case you forgot how to do scientific notation. It's a super small p-value. If I used the chi-square CDF method, I ought to get this same amount. I will check that in just a minute. But I want to talk about this contributions row. Do you know what this is? What's the 17 and the 6.86 and all of that? What are those numbers? Those are the same numbers that are right now in my list 4 because they are the same as this and all the other contributions to chi-squared. So sometimes you might need those numbers, and we'll talk about that in lesson 11.1c, why you might need those numbers. All right, so I'm just going to make sure that if I do chi-square CDF, I went from the bottom because it was faster to get there, and you did the chi-square value and 999 and 4, you should get the same answer, we hope. Oops, it doesn't like that because it doesn't know what my answer was, apparently. Let me do that again. Actually, I'm going to just do it again by doing this and typing in my, what was it, 48.17. Okay. Yeah, that's about the same. Really, really small p-value. It's approximately 0. And then we write a conclusion. Conclude. Since p is really, really small and it's way less than 0.05, hopefully you remember this. I hope you have this part memorized. Since it's small, we reject the null, that, and then you put your context. What does the null say? The null says that the age distribution for landline owners matches the census proportions. Well, it doesn't match. That's amazing. The age distribution of landline owners is the same as the population. So I'm going to stop there, but a tiny preview of 11.1c. In 11.1c, we'll talk about what more you could say about this. Like, we could figure out which ages are more likely to have landlines, which ages are less likely to have landlines. We could write about that too, but we're going to put that off till the next lesson. So for now, just the 4-step test. I spent a little extra time talking about the calculations and how to make the calculator do that. And we'll come back to the what more can you say about it in the next lesson.